Well, hello, everybody. Thanks to the organizers of this microfluidics and porous media session. This talk concerns micro and nanoparticle interaction with surfaces and retention in granular media, but it tries to honor the goal of the session by examining multi-scale processes. This is work done by myself and my graduate students, Cesar Ron, Anna Farnsworth, and Kurt Van Ness. I'd like to introduce a continuum scale issue that we're trying to address through nanoscale interactions. And so these are breakthrough elution curves on the top row and profiles of distribution of colloids from the source on the bottom row. And I'm calling these nano and microparticles colloids more generally for ease of reference. We're doing experiments in medium sand or glass bead granular media with 1 micron colloid microspheres in this example. And there's 3 pore volumes of injection of the microspheres and then 7 pore volumes of elution. And what you can see is that there's a characteristic steady state breakthrough corresponding to the injection period. And under conditions that are called favorable, that is conditions where there's no repulsion between the colloids and the granular media surfaces, that's called favorable because there's charge attraction there. There's no repulsive barrier to their attachment. And you can see that the steady state breakthrough is 99% of the population has been removed. In contrast, under conditions where the 2 surfaces are like charged, which is typical of the environment, of environmental conditions, and both surfaces tend to be negatively charged, there's charge repulsion, and that greatly decreases the amount of retention. The breakthrough is much higher. And the breakthrough increases with decreasing ionic strength for reasons I don't have time to go into, but that are well known in terms of their influence of particle surface repulsion. In the bottom row, though, you can see under favorable conditions on the right side, you have a log linear decrease in the colloid concentration as it moves through the porous medium, and that reflects the compounded loss of colloids as they move from grain to grain. In contrast, under unfavorable conditions to the left, you can see that the log linear decrease predicted by the red simulations don't match the experiments. And to match the experiments, we have to simulate with a decreasing KF. That is, the population becomes less prone to attachment as it moves through the media, which is a very important challenge for water resource protection and prediction for the purpose of remediation. So we want to understand what's controlling this continuum scale behavior. And to do that, we represent the porous media, the granular media, with a physical model. If you look at the flow fields in granular media, you can see that an important attribute with respect to particles or colloids is the impingement of flow on surfaces, specifically forward flow stagnation points or zones on grains where the flow is directed towards the surface and it diverges and then converges on a rear flow stagnation zone. And that's represented in these so-called haplospheres, where the flow has that characteristic in a fluid shell surrounding a grain. Now, this representation lacks grain-to-grain contacts, but preserves other elements of the flow field. And so in filtration theory, we recognize that a fraction of the population is removed at each grain. That fraction is called eta. And 1 minus eta is the ratio of the effluent to the influent concentration. So that once you go through a series of grains, then the effluent to influent concentration ratio is 1 minus eta to the power of the number of collectors. And that's the log linear relationship, the compounded loss that results in the relationship we see under favorable conditions. So why under unfavorable conditions we don't see that? And if we do force and torque balance simulations on a representative grain in a haplosphere and cell collector, even for modest repulsion, something on the order of 10 kT in terms of energy, we see no attachment. And environmental conditions predict barriers much larger than that, typically. And so it's long been invoked that there must be nanoscale heterogeneity on surfaces that allow local attraction and allow attachment. And that's shown in the image to the right, where we have included nanoscale heterogeneity in our simulations. To actually quantify that heterogeneity, we need to compare simulations to experiments. We use software that is available publicly called Parti-Suite. It's available on our website, wpjohnsongroup.utah.edu. I encourage you to take a look because we have the extended DLVO simulations with and without heterogeneity and the particle trajectory simulations with and without heterogeneity. So when we're trying to ascribe heterogeneity to a surface, the resolution depends, of course, on the analysis that we perform if we're trying to measure this directly. And the relevance of what we see to colloid transport isn't straightforward. So by coupling our simulations to experiments, we're trying to back out what scale and surface densities of heterodomains, that is nanoscale zones of attraction, are relevant to colloid transport. And we can constrain this because of the impact of the zone of interaction between colloids and surfaces. Because the interactions decrease drastically with separation distance, there's a finite zone across which these interactions are significant. And so we can recognize that the zone of interaction scales with increasing colloid size, that is, with the increasing radius of curvature. And so, as schematicized in the red, yellow, and blue, we have different zone of interaction sizes for different size colloids. And the green is a heterodomain, a zone of local attractive charge. And what you see is that it occupies only a small fraction of the ZOI, of the large heterodomain, but occupies a large fraction of the ZOI of the small, colloid. And so the net interaction is repulsive for larger colloids and attractive for smaller colloids. Likewise, it depends on the ionic strength of the solution. So for a given size colloid, the zone of interaction is larger at low ionic strength and smaller at high ionic strength. And so that leads to a net repulsive interaction at low ionic strength and an attractive interaction at high ionic strength for a given size colloid. To the zone of interaction, colloid diffusion is inversely scaled to size, and the surface interactions are also scaled directly with colloid size, so that a 0.1 micron colloid will experience significant diffusion. Looking at the cross section, it can diffuse, anywhere between a few nanometers to several microns back and forth away across the surface, like a mosquito. In contrast, a 7 micron colloid, once it gets near the surface, experiences much lower diffusion, but also much greater secondary minimum attraction and electric double layer repulsion. So it ends up pinned at the intersection of those two, the attractive and repulsive forces at the secondary minimum. And so it moves along the surface like a bloodhound. And 1 micron colloids are intermediate to the mosquito versus bloodhound behavior, leading to distinctive behavior. So we have zone and diffusion all contributing to behaviors. We've also learned that if we're going to ascribe heterogeneity to surfaces, we have to examine it on both surfaces, not just on the collector or grain surface, but also on the colloid. And so this schematic shows how we project colloid heterogeneity down onto a surface to see whether it falls in a zone of interaction, shown by the red circle, and to see whether it interacts constructively, that is, complementarily, to the heterodomains on the collector, or whether they in fact superimpose and therefore cancel one another in a destructive interaction. Together can be used in simulations. The behavior emerges from simulations accounting for all of these, the heterogeneity as well as the forces and torques. And the results are shown here in these panels, where the blue circles are data under favorable conditions and the red triangles are data under unfavorable conditions. And the unfavorable conditions become increasingly unfavorable from the top left down to the lower right. That is, from the highest ionic strength, lowest pH, down to the lowest ionic strength, highest pH. The surfaces are getting more and more negative. And you can see that this gap between favorable and unfavorable attachment increases with that increasing unfavorability, but also increases specifically for this nano to micro transition size range between 200 and 2,000 nanometers. And so by incorporating heterogeneity on both surfaces, we're able to capture this. And notice that the dotted line is for when we incorporate it only onto the collector surface. So we don't quite close that gap for the largest colloids if we don't include heterogeneity on the colloid. When we do include it on the colloid, which is shown by the red solid line, we close that gap, have a nice match to the data, and we do this by incorporating heterodomains on the surfaces ranging from about 25 to, actually smaller on the colloid, 5 nanometers up to about 90 nanometers. The collector or grain surface is shown on the top, and the colloid surface is shown on the bottom panel on the left. And they are both power law distributed. That is, there's order of magnitude more of the smaller heterodomains than the larger heterodomains because this represents kind of a natural clustering random placement process. And the resonance times for the nano to micro transition colloids are higher because they have lower settling, diffusion, and fluid drag, and so they take longer to get to the surfaces as well as to find heterodomains on which to attach. So we can take that resonance time information and scale it up to understand what's happening at the continuum scale. So the top panel here for the Hubble spheres is showing unfavorable conditions versus favorable conditions, and the dark green in the trajectory represents near surface transport. So that near surface resonance time is much longer before attachment under unfavorable relative to favorable conditions. And so we can look at the histograms of those resonance times, look at the overlap between favorable and unfavorable conditions, and note that there's a subpopulation under unfavorable that attaches fast, like favorable conditions, and one that attaches slow. Scale those according to the relationship shown here and described in Johnson et al. 2018, also a more recent one in 2020. And the point being that the fast attaching population can be treated according to a conventional rate constant, and the slow attaching population can be treated according to a rate constant modified by the fraction of slow attaching population, and those colloids that come around to the rear flow stagnation zone and potentially move to the near surface of a down gradient grain. But that probability is undefined in the Hubble setting. We need to use poor network modeling or similar approaches. And more important, we use the unconventional assumption that the fast attaching population is depleted. It is not replenished during transport. And so we ascribe that to incomplete mixing. Nice work by Diana and colleagues show that when a fluorescent tracer is invading from the left and displacing tracer-free fluid on the right, that you form zones of incomplete mixing that propagate from the rear flow stagnation zones of grains and actually, in fact, connect to the forward flow stagnation zones of down gradient grains, implying that you'll affect the mass transfer of colloids to surfaces. And so we're checking this to see whether or not this has an impact on what we see at the pore scale and the continuum scale, and explains our continuum scale deviations from log linearity. So this is all encapsulated in Parti-Suite. We encourage you to look at that. We've tried our approach on natural sediments, Central Sands, Wisconsin. We did experiments with 0.1, 1.0, and 4.2 micron colloids, and these following breakthrough elution curves on top and distributions from source on the bottom. And what you'll see is that the data shown in the symbols is not described well by classic filtration theory in the dashed lines. Classic filtration theory predicts much more retention, both in the breakthrough, much lower breakthrough, and much more retention at the inlet of the column than is observed in experiments. And in fact, in experiments, we see it distributed a much higher breakthrough and distributed across the length of the column. And so we can apply alpha to match the steady state breakthrough plateaus, and that alpha then predicts a distribution farther along the column, which is not a terrible description of the data, but there are significant gaps, orders of magnitude differences at places along the column, particularly near the inlet, particularly for the 4.2 micron colloids. And so the question is, could we use a scaling technique doing simulations in a Happel cell for these representative sizes. And what we find is that by doing what we propose, we do significantly improve the fit to these breakthrough curves and profiles. And we capture this transition from hyperexponential to somewhat more non-monotonic retention as we go from 0.1 to 4.2 microns in size. So point is that by putting discrete representative nanoscale heterogeneity into the model, we capture the reduced attachment that is observed for nano to micro transition colloids, and we produce the non-log linear retention profiles, doing that by upscaling at their residence times. So thank you for your attention, and maybe I'll get some questions from you in the session.